So we're discussing how to use distance-based methods to reconstruct phylogenetic trees. We've been seeing how the least squares and minimum evolution optimality criteria can be used to find the best possible trees. In essence, the idea is that we try to look through all possible trees. For each of them, we can compute this measure, this sum of squared differences, and the idea is then to pick the tree with the smallest sum of squared differences. That's the optimal tree. However, as we saw when we were discussing parsimony, that's a problem in that the number of trees grows explosively with the number of leaves. So for any realistic number of leaves, if we have more than 10, 15 leaves, it's impossible to look through all the trees. For distance-based methods, it's therefore possible, just as it was for parsimony-based methods, for the parsimony method, to do a heuristic search. It's exactly the same idea. You start with a random tree. You look for a set of neighboring trees by doing small rearrangements. For each of the neighboring trees, you can compute this sum of squared differences. You then pick the neighbor that has the best sum of squared difference, the smallest value of q, pick that as your new starting point, take the neighboring trees from that, again take the neighbor with the best value, climb one more step, and that way, using this hill climbing algorithm, you will gradually move towards better and better trees, essentially reaching a local and hopefully global optimum where you have a good least squares tree. So exhaustive search, one option if you have few tips. Heuristic search, another option if you have more tips. And that's possible both for parsimony and for distance-based methods. However, in the case of distance-based methods, there's actually a third way, and that is the group of methods known as clustering algorithms, clustering methods. Neighbor joining is by far the most widely used of these, and I'm going to explain how that works. The main idea in clustering algorithms is that instead of having an actual optimality criterion, instead of being able to, for any given tree, compute how good is this tree, and then use some method to find the best tree, the idea is that instead you have an iterative procedure where you gradually, step by step, build your tree. In the case of clustering algorithms, as always, in distance-based methods, the starting point is a distance matrix. The idea in clustering algorithms is that you then take two nodes that are, in some sense of the word, and I'll return to that, the two nearest ones. So you take two nodes that you believe to be adjacent. You put those together in the tree in the sense that you connect both of them to a common ancestral node. In the distance matrix, you now replace the columns and rows that you had for these two original tips. You replace that by a new column and row corresponding to your new ancestral node. You then just need to figure out what should I put in the distance matrix as the distance from this ancestral node to the rest of them. And depending on the method, there are different ways of doing this. You repeat these steps, each step putting together the two nearest nodes, putting together the two new nearest nodes, etc., gradually building up the tree until all the nodes in the tree are linked. This is very rapid. You just have an iterative procedure. You look at each node once, and you will end up with a tree quite rapidly. There is, of course, no guarantee that the tree you find will be the best possible tree. It won't be necessarily, at least, the optimal least squares tree or the optimal minimum evolution tree. However, empirically, these methods do seem to work fairly well, and they are definitely a lot faster. So, especially in situations where you want to rapidly get an overview of where your data set is very large, it might be an avenue worth exploring. So, in the case of neighbor joining, which is the method we'll just have look a bit closer at. As I say, each step in a clustering algorithm is about picking two nodes to put together, and they are the nodes that are, in some sense of the word, nearest. Now, in the case of neighbor joining, the sense of nearest is a bit peculiar perhaps, but it nevertheless works quite well. So I've put on this slide the entire algorithm, the entire recipe for doing neighbor joining. In principle, if you know how to to program a computer, you can take this slide and make a small computer program that will take as its input a distance matrix and then construct a neighbor joining tree as its output, just by following the steps on this single slide. So I'm going to just rapidly read through it. It may not make sense while I'm going through it now, but after I've done that, we will I will walk you through an example where we use the neighbor joining algorithm on a real distance matrix to build a tree, and you will see how that works out. So the idea in neighbor joining is that you compute a particular measure that you use as the basis for deciding which nodes to combine. First, for each tip, for each leaf, you compute this value called u, which is the sum of the distance from your tip to all the other tips divided by n minus 2, where n is the number of leaves. So this is essentially the average distance from your node, from your leaf I, to all the rest, except you divide by n minus 2 instead of by n minus 1. There's a deeper reason for why it looks like that. I'm not going to go into that. Now I'm just stating the algorithm. In neighbor joining, the idea is now to combine the two tips, I and j, where this expression is smallest. Okay? You combine the two tips, I and j, where the pairwise observed distance between the nodes minus ui minus uj is the smallest. For reasons that I won't go into again here, this turns out to be a good way of gradually building the tree. Once you have combined the two nodes, there are some things you need to figure out. You are combining the two nodes to an ancestral node, so you now need to figure out what is the length of the branch connecting each of these nodes to the ancestral node. In principle, you could just divide it in half and say half the observed distance will be put on either of the branches going out to either of these nodes. That's what's done in a method called UPGMA that we won't be discussing. But in neighbor joining, you instead use the expressions down here, which I again will not go into, for computing the two separate branch lengths. Finally, you need to figure out this new ancestral node that you just put in place of the two original nodes. What is the distance from that ancestral node to the rest of the tips in your tree? There's a formula for that also that's based on the observed pairwise distances in the following manner. I won't again go into that. Bottom line, follow these steps, compute u for each of the tips, compute this value for each pair of tips, pick the pair where this is smallest, compute new branch lengths from your two combined tips down to the ancestral node, compute branch lengths from your ancestral node to all the remaining nodes, and then run one extra iteration where you're now treating the new ancestral node as a tip. You repeat until all the nodes are combined. So let's walk through an example and see how that works. Let's say we start with this distance matrix. We have 4 sequences. We have these observed distances. Step number 1 is to compute the value u. So for each node, you take the sum of the distance from your node to the remaining nodes and divide it by n minus 2. In this case, n is 4. We have 4 leaves, so n minus 2 is 2. In the case of A, the distance from A to B is 17, A to C is 21, A to D is 27. So we add up those 3 numbers and divide by 2. That's 32.5. Same for B. 12 plus 18 plus 17 are the 3 distances from B to the remaining 3 nodes. Divided by 2, we get those numbers. Do the same for C and D. Now we compute this number for each pair of sequences. The pairwise distance between the 2 tips minus u for one tip minus u for the other tip. So in the case of A to B, for instance, the observed distance from A to B is 17. U for A is 32.5. U for B is 23.5. So 17 minus 32.5 minus 23.5 ends up at minus 39. Okay? We do the same for all the other pairs of sequences. In this particular case, we now need to find the smallest value in this table. So in this particular case, we actually have 2 equally small values. We have A and B and C and D. So we arbitrarily select C and D as the starting point for this combination and put them together in the tree. We've now decided C and D must be adjacent in the tree, so we connect both of them to some ancestral node, which I've called X on this particular slide. We now need to figure out what are the lengths of the branches connecting C and D to X. I showed you the formulas in the original algorithm slide. The formula for node I here, for instance, is half the observed distance between, in this case, C and D, plus half the difference between Ui and Uj. So the observed distance between C and D was 14, 0.5 plus 14, plus 0.5 times U of C, that's 23.5, minus U of D, that's 29.5. Plug in the numbers, do the computations, comes out at 4. Do the same for the other node, 0.5 times 14 plus 0.5 times U for, in this case, D minus U for C. Plug in the numbers, the value is 10. So according to this formula, we have now combined C and D, connected them to a common ancestral node, and we've computed the branch lengths from that ancestral node up to them. You'll notice that the sum of the branch lengths in this case, 4 plus 10, is 14. That's the same as the observed distance between them. So in this case, we have actually the patristic distance between C and D matches the one we observed originally. Okay, we now need in the distance matrix to replace the rows and columns for C and D with a new row and a new column for our single ancestral node. To do that, we need to compute the distance from our new node here, x, to the remaining nodes in the tree. A and B are the two remaining nodes that we haven't dealt with yet. There's a formula for that also. It's essentially these distances. I've put it up here. Plug in the numbers. You get the distance from x to A is 17. The distance from x to B is 8. So we put in those numbers in the distance matrix, and we can now delete the C and D rows and columns, giving us this new distance matrix. And we're now ready to run an extra iteration. Again, for each of the nodes in the distance matrix, we compute this value U. We take the distance, the sum of the distances from a node to the remaining nodes. So in the case of A, that's the distance to B plus the distance to X, 17 plus 17. We divide it by n minus 2. We now have 3 nodes, meaning we divide it by 1. 17 plus 17 divided by 1 is 34. For B, 8 plus 17 is 25. And finally, for X, 8 plus 17 is also 25. We now compute this other value for each pair of sequences, the pairwise distance minus U for one node minus U for the other node. In this case, the smallest value in this table is between A and B. We therefore combine A and B in the tree. We connect them both to an ancestral node. Again, we compute the two separate branch lengths using the formulas I showed you before. In this case, they turn out to be 13 and 4. And again, you'll actually notice that this means that the sum of these, 13 plus 4 is 17. That's the same as the observed distance between these nodes. So again, in this case, in this part of the tree, the patristic distance matches the observed distance. We now have just one remaining pair of sequences. We now need to replace A and B with the new ancestral node Y. We need to compute the distance from Y to X. That's again done using the formula that was on the original algorithm slide. It turns out to be 4. And at this point, we're actually done because we now only have these two nodes in the tree. So we just need to connect them with a branch which has the length that we just computed. So the result of all of this is the following. We started with this distance matrix. We went through the different steps in the algorithm, and you can see that we ended up with a tree looking like this. We have C and D together and B and A, and we have these branch lengths. The distance from A to B is 17. That's the same as we see in the tree, 13 plus 4. The distance from A to C is 21. 13 plus 4 plus 4, that's 21. The distance from A to D is 27. 13 plus 4 plus 10, that's 27. Distance from B to C, 4 plus 4 plus 4, that's 12. That also fits. Distance from B to D, 4 plus 4 plus 10, that's 18. And finally, the distance from C to D, 10 plus 4 is 14. So in this particular case, the neighbor joining algorithm actually gave us the perfect answer. There's a perfect match between the observed distances and the patristic distances. That will not always be the case, in particular for larger data sets and for cases where it's not possible, of course, to find the best possible tree. But often neighbor joining does give reasonably good trees. It will not guarantee that you find the best tree, though.